Hello, can I be heard?
Yes, it can be heard.
Okay, okay. Hello, Sri.
Welcome, welcome.
Hello, hello. Yes.
I hope you can see us and hear us.
I can see you. Yes, I can see you. I can also see Amitabha has joined this group, this talk. Hello, Amitabha.
Not Amitabha, Amitabha Lahiri.
Yeah, but Amitabha Raychaudhuri, Professor Raychaudhuri has also joined.
Yes, I can see him. Amitabha.
Thank you, Sreerup. Yeah, I'm looking forward to this talk.
Yes, thank you. Thank you for attending, Amitabha. It's always a great pleasure. Makes me nervous, though, of course, to think over times.
No, no.
I can see you. Yes, I can see you. Yes. Rajiv, should I share the slides to begin with, or you'll have some introduction and then I'll do that
Yeah,
afterwards?
but Amitabha will have some introduction and
Yes, I can see.
very special visit. So we'll have some
Okay.
introduction.
Yes, thank you. Thank you for attending, Amitabha. It's always a great pleasure. Makes me nervous, though, of course, to think over time.
No, no. Come on, Sreerup. Come on. I'm looking forward to this talk. I've heard very good things about something similar even elsewhere.
Should I share the slides to begin with, or you'll have some introduction and then I'll do that? Yes.
So this is for, it's 4 o'clock. So I think we can start. People will keep joining. And today, actually, our students' interview is going on. We tried our best to finish by 4, but, some people will be joining a little late. Good afternoon, everybody. So this is a special lecture series. As you know, India is observing the year-long celebration of 75th year of independence. And as the country celebrates Azadi Ka Amrit Mahotsav, marking the 75th independence, one of the major themes of this celebration is the role of scientists in the freedom struggle. Keeping this in mind, SNBO Center is organizing a series of talks on illustrious Indian scientists in the pre-independence era, depicting the heritage of our science and technology in that era, and trying to demonstrate that in spite of this British influence, through various suppression, ignorance, how Indian scientists excelled in that colonial time. And many of them were great visionary, like Acharya P.C. Ray, who apart from eminent chemist and educationist, was also an industrialist, being the founder of Bengal. So very much in line of something the modern India is thinking. The very first talk of this series will be given by Professor Sreerup Raychaudhuri from TIFR on the life and work of Professor Satyendra Nath, whose name half of the fundamental particles of this world is known, and on whose honor our center is named. Nothing can be a better start than these. Professor Sreerup Raychaudhuri, today's speaker, apart from his research as a particle physicist dealing with electroweak interactions, supersymmetry, techniques to search for new particles, are also interested in the history of science as science communicator. And it is my pleasure on behalf of SNBO Center to invite him to deliver the talk. But before I start, before Sreerup starts his talk, I see that our governing body chairman, Professor Jagtap, is also present in the audience. So, Professor Jagtap, would you like to say a few words on this special occasion?
Thank you, Professor Sahadas Gupta.
Yeah.
Welcome to Professor Raychaudhuri. It's indeed a matter of great pleasure that SN Bose is starting this lecture series. And the first lecture is on Professor SN Bose. Well, as Professor Sahadas Gupta said, that India's journey in science is inseparable from her journey towards freedom. And this is what gave a great age to the Indian science. The golden era of Indian science indeed lies somewhere there. And on this particular occasion, 75th anniversary, we need to remember all of them and their contributions to science, the contribution to the India, the intellectual India that we see today. And also important is to take some lessons from there. In spite of the racial discrimination, intellectual separation, and so on and so forth, these greats really did something marvelous to put India's name at the forefront of science and technology. So with these words, I wish this series all the best, and let's begin this.
May I now request start the lecture?
No, I can't hear you. Your voice is breaking.
So, Professor Sreerup Raychaudhuri, can you please share your slides and start the lecture?
Yes, yes, I'll do that.
Oh, thank you.
Has my screen come?
Yes, it has come. It has come.
Is it full screen now?
Yes, it is.
Okay. So thank you, Tanushree, for that very warm introduction. I'd like to thank SN Bose Center for inviting me to give this talk. Thank you, Professor Jagtap, for that warm introduction and welcome. And also should also thank, of course, one has to give my respects to my guru, Professor Amitabh Raychaudhuri, who has been kind enough to be present here, and to my friends. I can see Amitabh Lahiri, Monu Mathur, and others here. So thank you, all of you, and thank you also all the young people who have been attending this colloquium. So without more ado, I will start this colloquium. So it will be on the life and work of Satyendra Nath Bose. We have all heard of him, but perhaps we don't know so much details about his life and work. And in this picture, you see a picture of the young Bose, and he is surrounded by some colors. Now that is not an advertisement by Pepsi. That happens to be the simulation, computer simulation of a Bose-Einstein condensate. So, which of course follows his name. So let me go back, take you back more than 100 years to this period, 1905 to 1935, which was described by George Gamow as 30 years that shook physics. And of course, it is the story of quantum theory and relativity which have changed the way forever in which we look at nature. Now, I will now show you a picture of several scientists. And these are the people who made this revolution possible. Now, when you look at this list, all eminent names, very famous names, there is one person who seems to stand out like a sore thumb. And that, of course, is the person in the corner here, Satyendra Nath Bose. He is neither racially similar to them, comes from a different part of the world, and he is the person who will be the topic of our discussion today. But these stories should begin at the beginning. So let's start there. And I take you back to the 19th century, to Europe, and to the city, beautiful city of Munich in the 18th century. That's a picture of Munich with its famous cathedral. And I take you to this gentleman whose picture is in the center holding a prism, Joseph von Fraunhofer. He was a German optician who invented the spectroscope in 1814, more than 200 years ago. And what did he do? That when you looked at the sun through the spectroscope, of course, Newton had seen that if you look at the sun, you will get a spectrum of colors, the vibgyor, violet, indigo, blue, and so on. Now, what Fraunhofer found is that when you look at it through the spectroscope with a high resolution, focusing properly, you see all these black lines in the middle of the spectrum. And these lines are known as Fraunhofer lines. But if you look at the sun during an eclipse, suddenly those dark lines become bright lines. You can probably see, let's focus on these two yellow lines, for example, these black lines in the yellow. When it becomes bright, you see they become bright yellow lines. Let's look at, for example, this light in the violet, and you see it becomes a bright blue light. So what happens is that this spectrum gets inverted. So the Fraunhofer spectrum gets inverted. Now nobody understood what was going on. So only half a century later came the understanding, and it came with the discovery by a gentleman called Robert Bunsen of this humble instrument called the Bunsen burner, which I suppose you have all used in the chemistry lab. So in the Bunsen burner, what you can do is you can dip some fiber in the salts of various elements and burn them and see what line spectra you get. Now what Bunsen and his student Kirchhoff found is that when you look at the light which is coming from the Bunsen burner, from the flame with different element salts in it, you find the line spectra which you get. You're getting line spectra, and they match with many of the line spectra of the Fraunhofer lines. So the understanding of this came from, it was worked out by Kirchhoff. He proved using thermodynamics that the absorption spectra and the emission spectra must be the same. And that's the famous Kirchhoff law. So the absorption coefficient and the emission coefficient bear a constant ratio. It's independent of what the material is, what the substance is. It's always the same because it's based on the laws of thermodynamics. And therefore, if you have a black body, that's one whose absorption coefficient is 1. It will have some emissivity of lambda. Of course, you don't need to write the 1. So this is a fixed quantity. If you fix lambda and you fix T, lambda is the wavelength, and you fix the temperature, then you get this constant. So the challenge is only to find out what this constant will be, or rather how it will vary with lambda and T. So to find the function lambda and T, which is also called the black body spectrum. And once you understand this, you understand why, of course. So therefore, the explanation of the Fraunhofer spectrum is simply that there are all these elements are there in the solar atmosphere, the corona, which you see as a sort of bright cloud around the eclipse, and that's the one which is absorbing the light and giving you the Fraunhofer lights. Okay, so the first people who actually did a detailed measurement of the black body spectrum, I'm showing you a modern graph, but there were these gentlemen, but I will show you their graph also, but Loomer and Pringsheim, and they did detailed measurements to see how the black body spectrum varies. So this is how it varies as the wavelength goes up or the frequency goes down, whichever way you want to think of it. So when this happens, you will get a rising curve and then it falls off again. So the first person to try to explain it was a gentleman called Wilhelm Wien, and he found a formula which seemed to match for small wavelengths, but which became very poor for large wavelengths. And this was, so Wien's formula sort of worked at this end, but clearly it was not the right answer. A better form, it was sort of empirical. A better formula was discovered by the British scientists Lord Rayleigh and Sir James Jeans. So their formula, this Rayleigh-Jeans formula, it happened to do exactly the opposite. It worked well at the upper end of the spectrum. I'm trying to match this 7,000 Kelvin. It worked well at the upper end of the spectrum, but as you went to the lower side, to the small wavelengths, that is large frequencies, it just grew and grew. So of course it went far away from the actual curve, and in fact this went up to infinity when you went to wavelength 0, which is something known, that's the ultraviolet end. You can see violet, and beyond that is ultraviolet. So on the ultraviolet side, it led to what's called the ultraviolet catastrophe. The total integral became infinite. So of course, a black body doesn't emit an infinite amount of energy. So there was something seriously wrong. However, it was very well defined, very well derived. So the failure of the Rayleigh-Jeans formula, it gave a big jolt to classical physics at the turn of the 20th century. And I'll try to explain to you why. Because Kirchhoff, in proving his famous law, he has shown that the radiation confined inside a cavity. So imagine a cavity, there's a small hole and radiation comes here and it keeps getting reflected around, so it stays inside the cavity. So he showed that this cavity radiation has the same spectrum as the radiation emitted by a black body. So you simply find out the spectrum of the cavity radiation. And Boltzmann, using this idea, he had proved that the radiation emitted by a black body per unit area is proportional to T to the 4, which is something which had empirically been defined and found by Stefan, Joseph Stefan before him. So today we call it the Stefan-Boltzmann law. So this idea was certainly correct. Now what the Rayleigh-Jeans formula did was it simply counted the number of degrees of freedom of this cavity radiation and gave them the same energy. So Rayleigh had counted the number of vibration modes of a standing wave inside a cavity. I mean, there's a simple calculation which people do for organ pipes and so on, even at the high school level. And he found that the number lying between a frequency nu to nu plus d nu is this quantity, 4 pi nu squared by c cubed, where c is the velocity of the radiation, which is the velocity of light. And then Sir James Jeans had suggested that you should add a factor of 2 because the light has 2 transverse polarization modes. So the energy can go into either of the modes. So multiply it by another factor of 2. And then Boltzmann had derived something called the law of equipartition of energy, which we will come back to. And that said that each mode will get this amount of energy, Boltzmann constant, times T. So multiply by that. So multiply all of these together, you get 8 pi Boltzmann constant, nu squared T by C cubed. So the constant into nu squared T. And this was the Rayleigh-Jeans formula. Simple, profound, and wrong. So you can see here that as nu goes to infinity, this goes to infinity. Infinite amount of energy being emitted. If you integrate this over all nu, you will get nu cubed. And therefore, again, when you take it from 0 to infinity, you will get an infinite result. So that was the big puzzle. What was going on? So of course it's wrong, but where could one have gone wrong? I mean, first of all, the wave nature of radiation was not in doubt. I mean, you could see diffraction patterns. For example, this is a diffraction pattern from a laser, but that's just to show you the picture. But you could see it through a microscope, diffraction patterns. Many of you must have seen it in the lab. Counting of standing wave modes is also simple. Even high school students do it. And polarization is also an everyday phenomenon, right? If you have a polarizing lens or a polarizing pair of goggles, you can see that polarization does happen. You can vary the polarization and see it. So that part can't be wrong. So then you go back to the most famous detective when you have a puzzle. And the most famous detective ever, Sherlock Holmes, said, it's an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. So what remains? The equipartition law is the only one which remains, so that has got to be wrong. But how? How can it be wrong? Let's look a little bit at details. So the quantity of energy which can go into any mode is arbitrary. So let's say it's a quantity E. The probability for this, simple, is given by the Boltzmann factor. So let's say exponential minus E by KT. All right, so the average energy would be what? The average energy is E times this probability function, integrated over all energy and divided by the total probability. All right, so I substitute for N. So it's e to the minus E by KT divided by e to the minus E by KT, both integrated over all energies. So you can do this integral. It's a simple integral, and this is what you will get. The numerator is KT whole square, denominator is KT, so the answer is KT. And this is the equipartition function. So this is what Boltzmann had got. So I mean, nothing simpler. What could be wrong? It was a big puzzle. So people did puzzle over this for some time, and the answer came from Max Planck, who in 1900, he made an inspired guess, or maybe a desperate guess, or we don't know how he arrived at it, but he suppose these energy values, instead of being continuous, so you do an integral, suppose you make them multiples of an energy packet. Suppose you make them integral multiples of some E naught, which is some fixed number, and n is an integer. Suppose you do this. Then, of course, this same formula which I wrote here, you will replace this by some discrete values, right? So instead of being an integral, it becomes a sum. So sum over the same E times the probability factor for n divided by the total probability. And here I've only substituted for En as n E naught, this formula, and same thing in the expression. Now these sums are also easy to do. They're sort of arithmetic geometric sums. And if you do them, you get this. So the numerator becomes this, denominator becomes this, multiply them out properly, and you get this formula, E naught by E by kt minus 1. So you get a different formula from the equipartition. This is a different kind of equipartition formula. And this is of course not equipartition. It's not same for everyone. It depends on the value of t. E naught being a fixed quantity. Now, okay, new kind of equipartition. Now, for small values of E naught, let's see what happens if E naught is small. If E naught is small, you expand this by 1 plus E naught by kt, keep only the linear term. The 1 cancels, E naught cancels, and you get back kt. So this was the Rayleigh-Jeans result. And Rayleigh-Jeans result was the equipartition theorem. So that means that if E naught is small, this reduces to the classical equipartition theorem. But where does that work? The Rayleigh-Jeans formula works for small values of frequency. And so Planck concluded that this small E naught must correspond to small values of nu. So at least to the first approximation, you could take E naught proportional to nu. So you write it proportional to nu as some constant h. And that constant, of course, today we call this Planck's law, and that constant is known as Planck's constant. So now, okay. So now we put E naught as h nu, and this is your average energy. H nu by E by h nu minus 1. And now if you want to write out the black body spectrum, you have, this is the Rayleigh factor, counting of standing modes. This is due to polarization. And now you multiply it by this nu factor. And what you get is this formula. 8 by h by c cubed. This h is, of course, this nu constant. And you get nu cubed by h nu by kt minus 1. The beauty of this is, of course, for low values of h nu, this will again become proportional to h nu by kt. So the nu will cancel, you'll get your nu squared, 1t will go in the numerator, that's the Rayleigh-Jeans formula. But for other values, it will change. This formula is known as Planck's distribution formula. And you see that it matches the Rayleigh-Jeans formula for low frequencies. But if you go to very high energies, then again you will see that this will dominate, this exponential will dominate and will again fall to 0. Therefore, there will have to be a peak in between. So this matches not only the qualitative, but also the quantitative features of the observed black body spectrum. If you integrate this over all frequencies, you will get something proportional to t to the 4. That's a beautiful calculation which one does in the bachelor's class. Moreover, when these are the actual data presented by Lumer and Pringsheim, and you see that the matching is almost perfect. So, if you got such matching in the laboratory, maybe your teacher will suspect you of having manipulated the data. It's such wonderful agreement. Okay, this solid line is for Maxwell is the Planck formula. The dashed lines are the Wien formula. So it's simply too good to be a coincidence. So therefore, we have to conclude that Planck's starting point, that the energy values, instead of being continuous, there must be integral multiples of an energy packet. This must be true. But how? How can you talk about the energy of a wave, which is a continuous thing? How can that be tied up in packets? It's simply against logic. Well, Planck, of course, he's a very clever man. He thought he had an explanation, and he related it to something you see in everyday life. You see, I've blown up the cavity here. So the cavity, of course, has walls, and black body radiation stays inside the cavity. So he felt that, there are oscillators in the walls of the cavity, and they emit energy only as packets. So it's a property of these oscillators. They can hold only finite amounts of energy, and they will sort of throw it out as a packet. So these packets will come out, and they will all merge. They will merge to form continuous standing wave patterns inside the material. So to give an analogy, you think of a tap. If you have, after all, how does water come out of the tap? It comes only as droplets. So if you turn down almost close the tap, you will get one droplet of the other. These are discrete droplets. But when a large number of them come out, then it looks like a continuous flow. So this was Planck's idea, that it's the container, it's the walls which are responsible for this, and that's why you're seeing this behavior. But alas for Planck, his own best friend, I don't have to tell you who he was, he killed the idea. How? Because within 5 years, he came up with this theory of the photoelectric effect. So the photoelectric effect, most of you know this, it shows that when you get this famous equation, but it shows that when energy is coming in, it's also absorbed as packets. So these photoelectrons which come out absorb a finite energy, h nu. So this theory shows that energy is also absorbed in packets. Now, of course, how does this fellow know, this electron know that the energy has to be made into a packet before coming? It must already be in a packet. So therefore, if energy is emitted as a packet and absorbed as a packet, then in between it must be staying as a packet. After all, before it's absorbed, who will arrange it into a packet again? It's not possible. So therefore, energy must be always remaining in these packets, which we call quanta. And the modern name for it is photon. Okay, this is just what I've written. Now, Robert Millikan, you must have heard of Millikan's all-drop experiment. So Millikan hated the idea. He found it so repulsive. And he was a great experimentalist, so he set up this beautiful experiment. The whole purpose was to prove that Einstein's equation is wrong. So he said, okay, what I'll do is go back to this equation. I'll measure this energy and I'll measure the frequency and I'll show that they are not proportional. So here is his result. So it's almost as good a straight line as you can get in any experiment. And it shows that indeed it is proportional. So today, this is the textbook experimental proof that Einstein was right. So Millikan, who started off by trying to prove Einstein completely wrong, ended up by providing the strongest proof that he was correct and that photons do exist. So Einstein, on the basis of this, won the Nobel Prize and had the last laugh. As a consolation, soon after, Millikan also got the Nobel Prize, and he was cited partly for this work. In 1923, some 7 years later, Compton found that these energy packets, not only do they carry energy, but they also scatter and cause recoil. So the photon comes, it hits an electron, the electron recoils. So if the electron recoils, that must be coming from conservation of momentum. So the momentum he found is equivalent to what a massless particle would have, h nu by c. And that means that energy packets also carry momentum. So now if they carry both energy and momentum, there must be particles of light. Now we have heard of particles of light before, haven't we? Newton's corpuscular theory told you there are particles of light. Then came all the theory of Huygens and Young and so on, showing that there was any. So once again, there was a question. How come we have both particles and waves? So this was the situation, and for many years, it remained a puzzle till the coming of quantum mechanics and wave-particle duality. However, in between, there were many attempts at deriving Planck's law, and all of them were based essentially on Planck's idea, the original idea of Planck, that it comes from some kind of interaction between the photons and the matter in the walls of the container. Or if it's matter equilibrium somewhere else, it comes from the matter. So the matter-photon interactions must be causing the this discreteness of the quanta. So after Planck, the next person to use it, so Peter Debye, in 1910, he tried to use probability theory to derive this. So he's the first to use probability theory of course already introduced by Boltzmann, but to derive the energy transfer from the cavity. Then Nathanson in 1911, a very unsung physicist, he actually showed that Planck's law assumes the photons to be indistinguishable. Of course, this is also the root thing of Bose's work, for which today we give the credit to Bose. Unfortunately, Nathanson had discovered in 1911, he published his paper in a Swedish journal in Swedish, and it didn't get the respect it had to. But that happens to many scientific discoveries. Then in 1914, Ehrenfest and Camerlingonis, they pointed out that Einstein's photons could not be these Planck's distinguishable quanta, so they have to be different things, and that caused even more confusion. Einstein himself tried to resolve this problem by combining Bohr's theory with Planck's oscillators, trying to understand how, that if the atoms are quantized, how photons interact with it. This gives you the famous theory of AB coefficients, which are important in the understanding of matter-photon interactions, especially when you have high intensities in a laser, for example, and that's part of regular studies today. Then came Pauli. So Pauli showed that if you have Maxwell electron, Maxwell means following a Maxwell distribution, electrons having a nonlinear interaction with the photons, you could get back Planck's law. And here, this is the energy density of the photons. This is the energy density of the photons before the interaction and after the interaction. So there is a violation of causality here, because how will the poor photon who is going to collide know what the energy density after the collision will be? But by putting this, somehow Pauli had found the right answer. And then Einstein tried to extend this further, Einstein and Ehrenfest, by replacing the Maxwellian electrons by Bohr atoms with energy levels. So this was the state of art. As you see, that all of these ideas, they all had some interaction between the photons and the matter, atoms, electrons, whatever you like. But they all assume the classical statistics, that is the e to the minus e by kt formula of Boltzmann. And that is where they were all wrong. The solution, when it came from a quite different part of the world. So just to show you how strange it was, let me remind you that all this work was essentially going on in this part of the world, in the Central Europe, in Germany, in Holland, and so on, with Ehrenfest. But the solution came from here. Solution came from far away, from a different part of the world, and that was sort of amazing at that time, that people thought that science is all happening in Europe, a little bit in America, but that you could have science from a colonized country was impossible. And that's the theme of my story. So this is a good point now to start and tell you about the making of SN Bose. So I will shift now from the background, scientific background, to tell you about the life of SN Bose. So let me take you to Kolkata, Google map of Kolkata. This is North Kolkata, and I take you to this point here, which is in North Calcutta. You see Hakibagan Market, Uttudanga here, and this Google map again. I take you to this place, which is in the Goa Bagan area. You see Goa Bagan Park here. You see the Scottish Church College, Hidua, in this area. And here to this road, which is called Ishwar Mill Lane. So this house in Ishwar Mill Lane is still very well preserved. And of course, the photo was taken quite some time back, which is why you see this man-drawn rickshaw. This house is where Satyendra Bose, or Satyendra Nath Bose, was born at 22 Ishwar Mill Lane in the Goa Bagan area on the 1st of January 1894. So 127 years since he was born. Now, his father, I'll show you by this cartoon, Satyendra Nath Bose, he was an accountant in the East Indian Railways. He was a highly cultured man. In those days, an accountant in the East Indian Railways was a fairly high position which an Indian could hold, because the upper positions, higher positions were all held by Europeans. And he was also he was interested in science. He founded a small factory manufacturing chemicals. And this had its repercussions later, as you will see in his son's life. And his mother, Amudini, she kept the house and she bore 7 children, of whom Satyendra Nath was the only son, and then there were 6 daughters. So that was sort of normal in those days. Bose himself had many children. Well, here is a picture of them in their old age. And if you look at the picture of Sreerup Nath Bose, you will see that his son later grew to resemble him. He'll show you those pictures later very closely. It's, of course, not unnatural. However, the young Bose, you see a picture of him at the age 11. He was educated till the age of 12 in local schools. He was a bright student and especially strong in mathematics. But even when he was a small child, his father would leave him a bunch of mathematical problems to solve. This is just a sample slate, okay, not a problem given to Bose. You leave him a bunch of mathematical problems to solve before leaving for office. And when he came home in the evening, they would all be neatly done. Now, this whetted the young Bose's appetite for more and more complicated scientific problems. So in some sense, this was really where he was, the fire in which he was forged. At the age of 12, he was admitted to the famous iconic Hindu school, the nursery of the Bengal Renaissance. And here you see this beautiful neoclassical building, which was Hindu school in those days. This building doesn't exist. It's been broken down, and you now see this ugly modern building, sort of more utilitarian, but certainly lacking all the beauty. But at Hindu school, Bose blossomed under the tutelage of his famous mathematics teacher, Upendra Nath Bakshi. And it is said he was a great favorite with Professor Bakshi, Dr. Bakshi. It is related that once Mr. Bakshi gave Bose 110 out of 100 in his geometry exam. Okay, not for solving this problem. I've just given this problem to remind you of how complicated these plain geometry problems could be. Because Bose had not just solved all the problems in the examination, but he had solved each of them in more than one way. So Mr. Bakshi said this boy has to get 110 out of 100. 100 is not enough for him. And he was very proud. He used to say that one day this young man will become like an Indian Laplace or an Indian Cauchy. Actually, he didn't become a Laplace or a Cauchy, but he became Satyendra Bose in his own right. Then Bose later joined. In 1909, he joined the Presidency College. And of course, it was then called Hindu College. And no, it was already Presidency College. Sorry. So here is the Presidency College here. You can see these buildings. This is College Square tank. And this is where the Hindu school used to be on this side. This used to be the Senate building of Calcutta University. Then on the left side is the Senate building of Calcutta University. And this is Hare School and Presidency College. So, of course, no second-hand bookstores at that time. So what he joined was the mathematics department. And then he won his MSc in 1915 in the mixed mathematics course, and these are his marks. So amazingly high marks. If you know Calcutta University, in one paper he actually got 100 out of 100. And I later found out that this was not in his mathematics paper, but this was in applied physiology. So that's interesting. But 98 and so on, 298 and so on, 736, amazingly high marks. So not surprisingly, he stood first and won the gold medal of the university. Now in 1914, while still studying for his MSc, Bose got married. His bride, you see that bridal picture, of course, artificial color, was Ushabati Ghosh, daughter of a prominent Kolkata doctor. Doctor was, of course, rich, as you can see from the ornaments which the bride is wearing. But, you know, it is interesting that in those days it was customary to take a lot of dowry. And, you know, say, let the father-in-law send his son-in-law abroad to study. But Bose refused to take all that. All he said was that I have some 200 friends. Please invite them all to the wedding fest as Borjatri. So that was done. But otherwise he refused to take any money. And Ushabati Ghosh, or Ushabati Bose, as she became, she was 11 years old at the time of the marriage. That was sort of common in those days. It was not surprising. Later she bore her husband 9 children, 2 sons and 5 daughters, survived into adulthood. 2 infants did not survive. But Mrs. Bose was a very gracious and uncomplaining hostess to her husband's friends, because Bose was a very, very jovial and convivial person. So he had friends dropping in all the time, and he would typically say, "This so-and-so friend will stay to lunch, we'll stay to dinner, we'll stay 2 days." And Mrs. Bose was always very gracious and welcomed them and gave them sumptuous meals and so on. So she was very popular among Bose's friends for that reason. I showed you a picture of Bose as a family man in his old age. This is the old age Bose. So you now see that he looked very similar to his father when he grew old. This is the lady when she grew old. Sons, daughters, grandsons, sons-in-law, daughters-in-law, big family. This is not all of them, there were more. Okay, so coming back to the period, once Bose has passed his MSc, all right, done, then what? No job. He found himself unemployed like so many others. So what he did was many another person would do. He was married, he had about to become a father. So he started earning a living by doing private tuitions. Okay. So only one of his students became famous, but not probably because of Bose's tuition. But he was the young heir of the Gauripur state, princely state now in Assam. His name was Pramothesh Barua. And of course, he was remembered as one of the early film stars. Here is a poster of Pramothesh Barua and Devika Rani in the first version of Devdas. But the reason why, of course, I don't know what kind of a student Barua was, but Bose used to get 200 rupees per month for this, and that was literally a princely sum, as you will see in a moment when I show you some other figures. But then, came a lucky break. What happened was, Sir Ashutosh Mukherjee, he was a mathematician who had then become a jurist, a lawyer, and a judge. He became the second Indian Vice Chancellor of the Calcutta University in 1906. And among many other reforms, he started, before that, the university used to conduct only undergraduate programs. There were only colleges, and you could get a BSc or a BA or like that. But to do a postgraduate degree, you had to go abroad. But it was Sir Ashutosh who started the PG departments in physics and chemistry. And the physics department started in 1915, and that was the very year when Bose and his friends were graduating. Sir Ashutosh then persuaded two of his rich lawyer friends to donate generously for these two new departments. So these two generous gentlemen, if you go to the Science College today, you will see their statues right in front. Sir Rashbari Ghosh donated 21 lakhs. And Sir Taraknath Palit, in whose name the building, who donated his house also, donated 14 lakhs. And we must remember that this is 1915, and at 1913, Ramanujam wrote to Hardy saying that I am a clerk and my pay is 20 rupees per month. So you could survive on 20 rupees per month at a time when these gentlemen were donating 21 lakhs and 14 lakhs. So if you convert them to current figures, it comes to 250 crores and 170 crores. And nowadays, it's almost impossible to get that amount of money even from the government of India. So you can imagine, first of all, how generous these gentlemen were. And secondly, how rich they were, how prolifically they earned from the legal profession. Let's come back. With all this money, Sir Ashutosh built up a truly stellar physics department. So who were the people? There was D.N. Bose, who became the Rashbari Ghosh professor in 1914. In 1917, C.V. Raman joined as the Palit professor. Prashanta Mahalanobish was already in Presidency College. The young people who joined were Dignath Shah, S.N. Bose. I haven't shown you a picture of Shailen Ghosh because I couldn't find it. S.K. Mitra, Shishir Mitra, and Vidhubhushan Rai, B.B. Roy. So these were the younger people, young Turks, and Satyendra was among them. Okay. What was the salary like? 600 per month for the professor and 1,000 per month for the Palit professor. These people, lecturers, got 125 rupees per month. So now you see that for his tuition, S.N. Bose was getting 200 rupees. So that's really a very, very high sum for a tuition. And of course, coming for a prince. And what did they teach? So Mahalanobish taught mathematics, D.M. Bose taught atomic physics, and our two friends here, Dignath Shah taught quantum theory, and S.N. Bose taught relativity, which was always a great love with him, and to which he came back again towards the end of his life. And then radio science, spectroscopy, waves and optics, of course, Raman would be teaching that. Anyway, If you want to know more about this, you should read this book, which is by friends of mine and many of you. Gautam Gangopadhyay and Anirban Kundu from Calcutta University, Rajinder Singh from Germany. They have recently brought out this book, The Dazzling Dawn, the Early Days of the Physics Department of Calcutta University. But then things changed in 1919 with the Jallianwala Bagh massacre. And it is really with the Jallianwala Bagh massacre that Indians actually turned against the British Raj. So you see that, there are thousands now. Indians came out, the millions and thousands, to demand freedom. And this started happening, with non-cooperation. You see a picture here of the non-cooperation movement of Gandhi and subsequent agitations. And, within some years, the British Raj was gone. Well, Bose was sympathetic to the national cause. He was always a good friend of the revolutionaries, but he did not participate in the non-cooperation movement as such. And in fact, Sir Ashutosh, who was the vice chancellor, he didn't approve of disorderly agitation. So he was sympathetic to the cause, but he also did not approve. But 80% of the students of Calcutta University responded enthusiastically. They boycotted the classes. They publicly made bonfires of foreign goods, brought in Swadeshi and so on. So that story, of course, we have learned, we'll read elsewhere. Now, in retaliation, the government of Bengal, they threatened to withdraw all the financial support to the university. I mean, that is how governments respond, unless the university agreed to 8 conditions, which Sir Ashutosh described as humiliating. And they would basically give the Sarkari officials complete control of the university's internal matters. So those of you of us here who are listening to this and who know anything about administration of science will know that this is a long fight. I mean, it hasn't changed after independence, it continues. But Sir Ashutosh, of course, he was known as the Tiger of Bengal. He fought this tooth and nail, but by 1924, he was dead. And he was succeeded by somebody who basically gave in to all those 8 conditions. But at that point, when the financial support was being threatened to be withdrawn, some of the jobs would then go, which were financed by them. Among the jobs was that of Bose. So in 1921, Bose found that even though he had not participated in the non-cooperation movement, he was likely to suffer for it by having his job withdrawn. Now, at this same time, Sir Philip Hartog was given the job, so he came from Oxford, he was given the job of setting up a new university at Dhaka. And, he handpicked Bose and some other bright sparks, including R.C. Majumdar, J.C. Ghosh and others, persuaded them to move to Dhaka. And Bose, because his own job was not certain, he decided that, okay, he would move to the University of Dhaka. He got a promotion then. He would be offered a reader position instead of a lecturer here. What you see here is the famous Curzon Hall of Dhaka University. This is, the physics department is on this side. And he was given a bigger salary. Instead of 125 rupees a month, it was 400 rupees, increment of 50 rupees per year, going all the way up to 1200 rupees per month. So clearly a better deal. And so Bose decided to make the long journey from Calcutta to Gualando Ghat, there by steamer down the Padma River to Narayanganj, and there by train again back to Dhaka. So he moved to Dhaka. But there, life as a pioneer is always hard. So here is an example. Writing to his friend Nignath Saha in 1921, Bose wrote, "It has been well over a month since I moved to your part of the country. Work has not yet started," and so on. On the table of the sahibs are scattered lots of nickel prisms, lens and eyepieces. It would require a lot of research to determine which belongs to which apparatus. We do suffer from lack of journals and so on. They are talking about having a separate science library. So very, very, very rudimentary, and part of his job was to build these up. So in fact, his job was to teach thermodynamics and electrodynamics, and at the same time set up laboratories and buy books for the library. Then 2 years later came a big jolt. Again, the Sir Philip Hartog and the Dhaka University got into bureaucratic wrangling with the Bengal government. So again, the government cut money. And Dhaka University faced a financial crunch. And among other positions, from having this regular appointment, Bose's appointment was changed to a 1-year contract on a fixed salary, no increment, and no promise of continuation. So of course, both fought hard to keep his job. he wrote to the YVC saying that, if you go along like this, I'm going to leave. He says, I'm afraid I can't give any undertaking to serve till 8th October. If the university authorities persist, I shall have to seek for a job elsewhere. So, Hartog wrote back sharply saying, look, you've got a job, you're being paid much more than you were being paid there, so just shut up. But he was a fair-minded man. So in March 2024, he chaired a committee which gave Bose this permission. Mr. S.N. Bose to continue his work as reader till the end of the present session, that is till the end of September. Then to be granted 2 years study, till the end of August, a 2-year study leave from the beginning of September 1924, and to receive a total advance of 13,800, which in those days was enough to spend 2 years to travel and to spend 2 years in Europe. So it is Dhaka University which gave him the money to go to Europe. But it was while all this tussle was going on, amid all this uncertainty of what his future was going to be, that Bose wrote his famous paper on black body radiation. So let me come to that and I will come back to the story later. So Durga Puja of 1923. So Meghnad Shah, who came from a village near Dhaka, he came home and naturally he visited his friend Satyendra Nath. They were always close friends and the two had much to discuss, both personally and scientifically. And of course they discussed science because they were scientists. So Bose, who was teaching thermodynamics of black body radiation, complained that the theory of Planck was hard to teach to the students who kept asking awkward questions. So good message to students, please do keep asking awkward questions to your teachers. Who knows, maybe a great discovery will come out of that. Now, Meghnad Shah, who had recently moved to Allahabad University, Allahabad University was well endowed and they had a much better library. So they were getting the contemporary journals. So it was Shah who had informed Bose about these papers of Pauli and Weinstein and Ehrenfest, which had just come out. Bose had not seen them. And Shah, in the fashion of those days, he had gone to the library, he had taken those journals, and in his notebook, he had copied down notes from them. So he lent Bose those notes to look at. Now, I should let you a little bit, so that in as early as 1903, and then Fokker, Lorentz and then Fokker had shown that the momentum transfer between free electrons and radiation. So imagine that you have, imagine that the red things are photons and the other ones are free electrons. So the momentum transfer, when you put them together in a cavity, it can't take place if you have only radiation pressure. Okay, so radiation pressure was the only known way by which momentum transfer was known to take place. He showed that if that happens, you will never get equilibrium. It's too weak. But Pauli had showed that you could do that through Compton scattering. But in order to do that, he used the formula I showed you with this nonlinear term, which is violence causality. So Bose looked at those, and then, of course, I told you about the Einstein Ehrenfest calculation. So this is what they were trying to do. And Bose looked at those, and they all looked fishy to him. So then he decided to treat the photons purely as particles, forming a gas, just like you do with molecules of hydrogen, oxygen. You have your kinetic theory of gas. He thought he would treat the photons purely as a gas. This was a departure because he was not relying on their interactions with matter, photons only. Now, the statistical behavior of gas had already been worked out by Maxwell and Boltzmann. That is well known, Maxwell-Boltzmann statistics. And here is what we do. What we do here, treat the phase space of a gas. See, it's a multi-dimensional space. I'm drawing only one coordinate, x and px, and you create this little phase cell with a delta x into a delta px. It's like a little box. And of course, this will actually be 6-dimensional because there'll be also y and z. I can't draw that, so I'm showing you two of them. So imagine a phase cell, and if the area of this is delta, this delta x and delta p gives you a volume delta, then the phase cell will actually be volume delta cubed, because if you introduce delta y, delta py, and delta z, delta pz, it's a 6-dimensional space and the volume will be delta cubed. Now, the number of phase cells lying between energies E and E plus delta E is simply given by this formula. You divide, so this is the number of volume of that area, and this is divided by the volume of each cell. So that's the number of phase cells. Then you calculate the statistical probability of distributing n number of particles for a given energy E among these cells. For this, what you do, you simply count the number of configurations created by putting any different particles in the number of, so there are so many phase cells, and there are so many particles. So small n is the number of particles, capital N is the number of phase cells. So how can you distribute them among those cells? So it's like distributing a set of colors. So each of these boxes corresponds to a value of E. And each of these E's, there's a small number n in each of them. So how would you distribute? And small n is the number of colored balls. So the balls are all different. You can distinguish. So this is one configuration. You can distribute them in a different way in other boxes. Put more of the sum in from this box to that box and so on, and you would get it. So having these large number of compartments, large number of boxes, you can calculate. This is a well-known calculation, and this is the answer. You can do it in combinatorics. The number of configurations given by capital N, which is the number of boxes to the power of the number of particles divided by factorial of the number of particles. Okay, then what you do is that when you take all the energy boxes, you have to multiply by all the number of, and now you have the possibility that you could redistribute each particle. So you have to multiply by all the permutations of particles among themselves. So you get this form. So this is the total number of configurations. And then, of course, if instead of a sum, you could, the total number is, of course, the sum. So the sum can be an integral if energy varies constantly, but it doesn't have to be. So now you find the entropy of the system using the famous law of Boltzmann. Boltzmann told you what to do. The entropy is related to this total number of configurations by k log of that, and that's the entropy. So in this case, this is the total number of configurations. So you take k log of this. And so what is the unknown here? It is what this n is, where the particles went, how many particles went into this. But the second law of thermodynamics tells us that when the gas is in equilibrium, the entropy must be maximum. So the Ne, small n, must be distributed in such a way as this quantity should be a maximum. However, this is not a free max, so you can just maximize this. However, you have to have these two conditions. The total number is fixed and the total energy is fixed. The total internal energy of the system is fixed. So given these, now you do the mathematics, and this you will get this distribution. Of course, you have to make the approximation. Number of particles and states is large, but you get this distribution, which is known as the Maxwell-Boltzmann distribution. So energy goes as minus C by kT and T, and then notice something, that the delta has cancelled. There is no delta in this final result. So now you could happily take delta to 0 and say, okay, energy and space and momentum, they are a continuum. There is no reason to make them discrete. It was just an artifact which I used to do my calculation. A limiting case, let's say. Now for an ideal gas, of course, where the particles don't interact, then these are all free particles. So E is half mv squared, and we get the famous Maxwellian form. Well known, I won't spend time on that. But this is the Maxwell distribution. And of course, there are various things which test it. For photons, now Bose made 3 crucial physics assumptions. Now these are all physics assumptions, no mathematics. The first one is that he took this phase cell not to be some delta which goes to 0, but to have area of Planck's constant. So he put Planck's constant here instead of delta. And what does that mean? That means delta x into delta p is h. Have you seen this? Of course you have. This is the Heisenberg uncertainty principle, which Heisenberg quoted in 1925, but it was taken 2 years before Heisenberg had thought of it. Now, Bose didn't go have the same arguments which Heisenberg had, okay, but he took the result. Perhaps he didn't really know what he was doing when he took the result, but certainly he took it. So the uncertainty principle was first used by S.N. Bose in his derivation. That's the first result. So he took this as H, and you'll see he was very proud of it. We'll see that in a moment. The second physics assumption was that the photons are not just identical, but they're indistinguishable. Now, why would two particles be indistinguishable? You can distinguish them by their coordinates. Only if you don't have fixed coordinates, and that's because they have some wave nature, that can only happen with this. So this indistinguishability would really mean that instead of all the particles being colored, they're all identical. So if you move this particle to here and this particle there, there'll be no difference. So you have to do the counting in a different way. And this indistinguishability is really the same as the wave particle duality, which came again only the next year. Again, Bose used it without going through the same argument. The arguments of de Broglie are brilliant, but Bose didn't have all those, but he assumed the same result. Now this combinatorial problem had to be done afresh. So taking the fact that interchange of the balls in the boxes gives the same configuration. Now this is not a new problem. It's an old problem of mathematics. We can date it back to the 2nd century BC with the work of Pingala. Okay. And then with the various famous people, Omar Khayyam, Fibonacci, up to De Moivre in 1711. No magic in this. Well known to mathematicians, and Bose must have immediately known the answer. And why is that? Because we remember that Bose was a brilliant student, and the algebra book which he worked out, and which we know he worked out the whole book, was this book by I. Hunter. It was the standard textbook for colleges and schools around the time Bose was a student. And here you see that this was 1889. And here on page 536 of this book, problem number 811 is exactly this problem to find that. So Bose knew the answer. And this is the answer. It's slightly more complicated, but it is the number of boxes into number of particles minus 1 factorial by number of particles into number of boxes minus 1 factorial. So all you do now is repeat the same calculation, take all the energy boxes, so take the continued product of this. And if all these are photons in an enclosure, they are being absorbed and emitted all the time. However, so the total number is not fixed. So photon can be absorbed, emitted. It's not a fixed number like molecules. So go ahead and find the entropy. Same calculation with this Bose form here. Put it in the second law, same statement. Only earlier we had fixed total number and fixed total energy. Now we don't have fixed total number, only fixed total energy. So go ahead and do the maximization and you arrive at this distribution. So look at this distribution, the n is there in the numerator and this already has the Planckian form. So what did this come from? Only the assumption of the fact that the particles are indistinguishable. Now Bose's calculation of this NE was also novel and far-sighted because that's how we do it today. So for photons, he combined Planck's law and Einstein's mass energy relation to write this. He wrote this for the energy, of course, Planck's law and momentum. And of course, if you rewrite the frequency in terms of c by lambda, you get this. This was exactly what de Broglie had done, was going to do a year later. So having combined these, he took P as h nu by c. Planck had done the same, or rather Compton had done the same. So the number of phases, instead of this P, you replace it by h nu by c, you get this formula. 4 pi d squared d nu delta. And so now taken per unit volume, so you can divide her by the volume because he immediately got the same number of photon states. You see, if you take out the volume, what do you get? Number is simply the Rayleigh number. Notice, no stationary waves, no cavity, just photons counted in phase space, identical photons. So when you plugged in the statistical distribution with this, you put this formula for NE, and that's the formula. So the average energy multiplied by h nu, you get this. Very similar to the Planck distribution, except for a factor of 2. Okay, Bose got 4, Planck's distribution had, let me go back one second. Planck's distribution had 8. So now he made his third crucial physics assumption. See, he says these are particles, right? Photons are particles. So the only thing they can have is angular momentum. You've taken the momentum, you've taken the energy. It can only be angular momentum. So maybe they're spinning around their axis, either clockwise or anti-clockwise. So there's a factor of 2 depending on which way it's spinning. Now, of course, this is the concept of intrinsic spin, again, 1 year before Uhlenbeck and Gauss-Schmidt proposed it. Now, you'll see that this concept was messed up by Einstein, and he did not realize, Bose, how far-reaching these assumptions were. So there are 3 major discoveries in this: uncertainty, wave-particle duality, and spin. But he had not worked those out in his mind in detail, but somehow he had some amazing intuition, so he was able to put these in. And he wrote it up in a very modestly titled paper, Planck's Law and the Light Quantum Hypothesis. And here I will show you, this is not his original manuscript, which is lost, but this is a manuscript where he wrote it up later. You see his signature there. He wrote it up for Einstein later, and this was found among Einstein's papers. It's in the Einstein archive. So you see the same kind of formula which I have shown you. But anyway, full of confidence, towards the end of 1923, he sent his manuscript to the Philosophical Magazine. That was sort of the top journal in those days. And he sent it for publication there. So in the way which journals do, the journal sat on his thing for 6 months. And after that, they sent back his manuscript with a very curt note saying, sorry, we can't publish it. The referee's note is negative. Your paper is wrong, so we won't publish it. And in those days, they didn't send back the referee reports. We don't know why the referee thought it was wrong. So, Bose was sort of desperate, and he decided to send it to Einstein. So, in those days, Einstein had become the editor of this new journal called the Zeitschrift für Physik, and people who couldn't publish their papers elsewhere would send it to Einstein. So most of them were correct papers, but Einstein was a patient man. He would read them and actually take them. So even de Broglie's paper or Kaluza-Klein paper, these were papers, Kaluza's paper, which could not be published elsewhere, was sent to Einstein, and he saw to their publication. So Bose wrote this letter to Einstein, and it's interesting to read this. He says, respected sir, I have ventured to send you the accompanying letter for your perusal, etc. Notice here, I have tried to derive the coefficient 8 pi nu square by Planck's law independent of the classical electromagnetics thing. So he says, he's not going to do waves. So he's very proud of this derivation. So it's important that he was proud of it. Then he writes here, I do not know sufficient German to translate the paper. If you think it's worth publishing, I will be grateful if you publish it in Zeitschrift für Physik and so on. However, Bose had actually translated Einstein's papers from German into English. So his statement that he did not know German was not correct. And Einstein realized that, because a guy who can translate your work from German into English certainly knows German. So he wrote back to him in German. And you see here, Leverhulme College and signed Einstein. And let's look at the translation. He was supportive, but he also defended his own work. He says, dear colleague, I have translated your work and communicated it and so on. And this was the translation. Plancks, and that's von Bose. He's not even quite sure what the name was. So he just wrote Bose, Dhaka University. And then you see here the H cubed is important. See, that's the one which is here. So he says, it signifies an important step forward. I liked it very much. You are the first to derive the factor quantum theoretically. And then he says, because of the polarization factor, not wholly rigorous, I'll come back to this, but Einstein gives him praise. He says it is a beautiful step forward. He added a note of support at the end saying, in my opinion, Bose's derivation signifies an important advance. The method used here gives the quantum theory of ideal gas, as I will work out elsewhere. Notice he doesn't say we will work out elsewhere. I will work out elsewhere. Come back to that. He neither invited Bose to collaborate, nor did he ask Bose to visit him at Berlin. He's publishing his paper, and now I will take it ahead. Okay, moreover, he changed Bose's idea. This, of course, there is no proof because the Bose's manuscript is lost. But Bose said it many times that I wrote about angular momentum, and he changed it to polarization. So Einstein changed it to polarization in the translation, and that's how you got this factor of 2, okay, and factor of 8 there. The only person who ever stood up for his spin idea, of course, he had won some recognition, was C.V. Raman. In a paper with Bhagavantam in 1931, he later wrote, we understand from personal communication by Bose that he had actually taken this plus minus H. Anyway, what happened here was that with Einstein's postcard, it helped to smooth the path to getting visas for Bose's Europe trip. So they were financed by Dhaka University, and for the German visa, because Einstein had written, his visa fee also was waived. So it did help. And so in September 1924, Satyendra Nath Bose set sail for Europe. But all his famous classmates, Meghnad Saha, Mitra Bose, they had all gone earlier. And the reason was simple. They had all taken the Premchand Roychand Fellowship, which was then gone. And Bose couldn't take the Premchand Roychand Fellowship because one of the conditions of that was that you had to be a bachelor. As I have shown you, Bose had got married very early, so he was not eligible for the PRS scholarship. So he had to wait till Dhaka University financed his trip. But anyway, he reached Europe, and on November 18th, he reached Paris. Now, why Paris? That's because in 1923, one RL Day, from Dhaka University had gone to work with Madame Curie at her laboratory, and Bose's mails were being sent to there, and he needed to stop there to pick them up. But not only that, he liked Paris. There was some cheap accommodation at the Indian Students Association, and some of Bose's old friend revolutionaries who had escaped from the British Empire to avoid arrest, they were there. So he had old friends, so he stayed there for some time. He was advised that if he wanted to work in Madame Curie's laboratory, he should first meet with Paul Lajoie, who is well known to be Pierre Curie's student and very close to Madame Curie. So in fact, Lajoie had read Bose's paper, he was impressed. So he welcomed Bose with open arms. And for many years after that, he was a friend and mentor for Bose. And he learned that Bose was interested in both crystallography, which was an up-and-coming subject in those days, and radioactivity. So he gave him letters of introduction, both to the great lady and to the crystallographer Maurice de Broglie, who was the elder brother of Louis de Broglie, the famous discoverer of quantum mechanics theory. Well, so Bose went to meet the great lady, and I show you this footage. This is real footage of Madame Curie in her lab. You see her, of course, in her old age, already, not really old age, but already suffering the effects of radiation sickness, so looking ill and tired, but anyway, sorry. Okay, so by then she was already famous, two-time Nobel laureate and so on. So she greeted Bose warmly, said, since you're coming from Lajoie, I will certainly allow you to work in this institute. But then, she spoke perfect English. So she said, Bose, you should wait till the new year and learn French. Everyone here speaks French. And, Dr. Day did not know French, so he had a lot of difficulty. So why don't you wait till the new year? You've come in November now. Spend 2 months learning French, and from next year you can work here. Bose later said he was so awestruck on meeting the lady, he forgot to tell her that for 10 years he knew French. He could read, write, and speak it fluently, but he didn't dare to open his mouth in front of her. So he just accepted that. So for the time being, he worked in Maurice de Broglie's, you see his picture here, laboratory, working with X-rays. And then in the new year, Madame Curie kept her word. He started working in the laboratory, and he kept working there. The days went into weeks and months, and he reveled in the atmosphere. He learned experimental techniques from these experts. He would discuss theory with Lajoie and Louis de Broglie, the young brother, and enjoy the company of Indian students and revolutionaries in the house at Rue de Somera. And he also made friends easily. For example, Bertrand Zadoka, here you see him here, a young cardiologist, and his pretty sister Jacqueline. So these people he made friends with them. They remained his lifelong friends. He was a friendly person. But meanwhile, he had written another paper, and Einstein had again translated and published this. And this had considered an ideal gas in statistical equilibrium with radiation. So he found that the gas molecules have a Maxwell distribution, the photons have a Planck distribution. All you assume is that the gas molecules are distinguishable and the photons are indistinguishable. And by then, Einstein had got Bose's name correct. He had SN Bose, but he got the place wrong. Romna is actually the location in Dhaka where the university lies. So earlier he had Dhaka University correctly here, but the name was wrong. This time it was the other way around. Anyway, so Einstein, of course, Bose, as soon as he had got there, he wrote to Einstein. He addressed him as master. Einstein was the great Einstein. I've been granted leave by my university for 2 years, so I don't know whether it will be possible for me to work with you. Of course, he wanted to go and meet the great man. And Einstein replied very politely, thank you for your letter. But again, he's still defending his idea that the Planck distribution is not due to photons alone, but there is some interaction. I am not in agreement with your basic principle concerning the probability of interaction and so on. However, he has published his paper. So apparently Bose had a third paper which Einstein refused to publish, but that's a different story. And meanwhile, Einstein himself, while he says I'm not in agreement with your idea, he was feverishly working on Bose's idea. So in 1924, he worked on the statistical distribution of atoms in a monatomic ideal gas, which really the only difference with what Bose's calculation is that you keep the number constant. So these are massive particles, and you get a massive boson gas. And that immediately has this phenomenon that the molecules cluster at the ground state, which is known as Bose-Einstein condensation. Now, these papers were by Einstein alone, you see, no Bose in this. But Einstein was generous enough to accept that the method he was using had been discovered by Bose, but he was not going to share this glory with some obscure person from Asia whom he had never met. It was in fact Paul Dirac who made Bose immortal. In 1926, he called the expressions Bose-Einstein statistics, and the other one for particles, which are restricted to only one per state, well, he called Fermi-Dirac statistics. And being very modest, he didn't call them Diracons, he called them fermions. So to match the fermions, these other things had to be bosons and not Einsteinions. So these names have stayed since. So in a sense, it was Paul Dirac who made boson's name immortal, not Einstein. But Bose himself, he never bothered about Einstein's selfishness. Einstein was the master. And so after a whole year in Paris, in October 1925, he was able to move to Berlin and meet his hero. This was the Kaiser Wilhelm Institute for Physics. Today it's the Max Planck Institute, I think, for radiation chemistry. But it, of course, took a lot of damage during the war, but it's been rebuilt in the old style. But this is an old picture. Anyway, I'll show you a little bit of footage now of the great man himself. Probably not taken there later, but good to see him, sort of. So through Einstein, Bose soon came to know the whole Berlin gang, and the very famous people. Max Planck himself, Walter Nernst, Hahn, Lisa Meitner, von Karman, Schiller, Wigner, De Bayer, Hermann Mark, with whom he actually worked, Haber of Haber's process. But everything revolved, around one great man. So he towered over all the others. And then in 1925 came the new quantum mechanics. And these were 3 papers by Heisenberg, born in Jordan, and then Heisenberg, born in Jordan. And there's a lot of excitement. So Bose is writing to Jacqueline Zadokhan, who was then a schoolgirl, but so he was writing. He says, everybody seems to be quite excited in Berlin, the way things have been on with physics. First, on the 20th October, Heisenberg spoke at the colloquium. Everybody is quite bewildered. There is going to be very soon a discussion of Schrodinger's papers. Einstein seems quite excited about it. The other day, coming from the colloquium, we found him jumping in the same compartment where we were, and forward he began to talk excitedly about the things we have just heard. We were all silent, but he talked almost all the time, unconscious of the interest and wonder that he's exciting the minds of the passengers. So you can see the excitement of the tribes. And Einstein suggested to Bose that they should collaborate on 2 problems. Again, you see Einstein is sticking to the old. Whether their new states imply some subtle interactions between the photons themselves. And the answer is no, it does not. There is interaction between photons, but it's too weak to matter. How could the transition probabilities of spontaneous and stimulated emission be derived in new quantum mechanics? Now, this problem was much too. So the first one was not workable because there is no such interaction. The second one requires a perturbative calculation, the dipole approximation. So quantum mechanics had to develop much further before these could be solved. So not surprisingly, Bose did not make any headway in either problems. So since he couldn't solve anything, he started working in Hermann Mark's crystallography lab, where he could do the work, continue the work he had been doing with Morris de Broglie. Of course, he visited Einstein regularly and had all manner of discussions with him, but these 2 problems remain unfinished. So there is no paper, no Bose-Einstein paper as such. And in mid-1926, he had to come back to India. Now, working with Einstein was not easy. Many years later, Bose opened up a little bit about his experiences with the great man, so, to a close friend. And he says, so this is what the friend says, Einstein had given him a problem to solve. Satyendra Babu told me, I thought about it for 3 days and then I went to see him with my solution. Einstein went through it and said, well, this is not wrong, but not the way I want it. This clue does not open up any new possibility. Please don't waste my time with such trifles. That is what the old man said. Satyendra Babu's mind seemed to go back to the past. Well, the truth is that Einstein was now 46 years old and he did not like being proved wrong any more than anyone else. And actually his intense creative period was more or less over. The Bose-Einstein work is actually the last work of Einstein which has lasted. However, of course, he was still the great Einstein, but whatever it is, Bose after that did not publish again in theoretical physics till 1939. So for 13 years, he stayed away from theoretical physics. So you have to draw your own conclusions from this. Anyway, now I will just quickly tell you, I'm well past my time, about the last years of Bose when he came back to India and he was sort of the sage. So I'll just show you the main milestones in his life. In 1926, he returned to Dhaka. Of course, he still didn't have a PhD, but he had reference letters from Einstein, Lajava, Havenbach. So they promptly made him professor and head of the Department of Physics at Dhaka University. After 1 year, he was also made Dean of Science. And as such, he set up laboratories in chemistry, optics, and crystallography and started publishing in these areas. In 1938, he was recalled to Calcutta University to take up the Palith professorship. He didn't take it up. Instead, Meghnad Saha took it. And then, of course, there have been many other people after that. But I'll take this opportunity to show you a picture, it's a very cherished picture of myself, of course, not just with, so in this was the head of department's office in Dhaka University. You see, of course, he had another very famous physicist, Professor Ashok Sen, and this is Professor Arshad Momen of that university. But I'll show you this board. Let me blow it up. And you see here, W.A. Jenkins, 1921 to 96, and then Professor S.N. Bose, 1926 till 30th September 1945. A long period. And then, of course, other well-known people. So you see here, S.N. Bose. So it was really a privilege to see this. And now, what are the kind of work which he did there? Well, here is some work he did. So you see in chemistry, electrochemistry, radioactivity, 2 works on statistics. This D2 statistics is the thing discovered by Mahalanobis, and he worked on that. Radiophysics. These are 2 papers on radiophysics. Then he comes back, studies in the Lorentz group towards more mathematical physics. This is certainly quantum mechanics, so being written as late as 1940, solutions of the Klein-Gordon, inhomogeneous Klein-Gordon equation. Again, chemistry, Dirac equations, so on. So you see that he worked on a wide range of things. Basically, he did whatever he really liked at the moment. In 1945, he accepted the Khaira professorship at Calcutta University, left Dhaka forever. By then, Hindu-Muslim riots and feeling of insecurity in East Bengal, it was soon to become East Pakistan, must have prompted this decision. For he really had come to love Dhaka. He had not planned to leave Dhaka. He sort of felt constrained that he would have to leave Dhaka. And here is his room in Dhaka University. It's been preserved exactly. This is his chair, and it says at the back, this is the chair used by S.N. Bose. And I had, again, the privilege of being able to photograph this. In 1947 came independence, second partition of Bengal. All these pictures, well, they only look too familiar nowadays, again, but these things happened. But while others who are his contemporaries became institution builders, Bose was perfectly content to remain the quintessential scientist. So, people like Mahalanobis, Raman, each built their own institutions. Sarabhai, Bhabha, J.C. Ghosh, Meghnad Saha. They all became institution builders, not Bose. He remained doing science. He was indeed nominated as a member of the Rajya Sabha, and he did accept it. But he remained a member till 1959. But he spoke only 3. But it's interesting that the speeches which survive are still relevant. One opposing judicial overkill, one on solving the refugee problem, and one on the role of the new formed UGC, showing you how little the country has actually changed. Anyway, he retired from Calcutta University at the age of 62 in 1956, and he was immediately appointed Vice Chancellor of Vishwabharati, the university set up by Rabindranath Tagore at Shantiniketan. But he could manage with the university, and wisely, he resigned after 2 years. He was elected a Fellow of the Royal Society in 1958, very late in his life. It should have happened long before, but actually it happened because Dirac visited Kolkata in 1957, and he was aghast to know that the great S.N. Bose was not FRS. So when Dirac, who was then the president of the Royal Society, went back and nominated him, that's how he became a Fellow of the Royal Society. In 1959, he was appointed National Professor for 5 years, and this position was renewed so long as he lived. Calcutta University made him Emeritus Professor and gave him a lab and grants to work through the Indian Association of Cultivation of Science. But by now he was 65, so aging, but he continued to train students in experimental techniques. Then, Another interesting thing in his life was he wanted to teach science to be taught in the mother tongue. So he founded the Bongyo Bigyan Porishad in 1948. And his experiences in Europe and Dhaka have colored his vision, also visited Japan. But anyway, this sort of remains unfulfilled. He was appointed president of the Indian Statistical Institute at age 73. He would remain president till his death. Then we come to 1974, which was Bose's 80th year, as well as the 50th year of the Bose statistics. So during this year-long celebrations were held in Kolkata and elsewhere, a long round of seminars, symposia, felicitations, and cultural programs. And characteristically, Bose himself was the most enthusiastic participant. So he felt actually vindicated. He said, now I feel I do not need to live any longer. He felt he had got all the recognition he wanted. I show you this little clip from a films division picture. Here is Bose speaking at one of those functions. It's old now, carries a stick. But unfortunately, he had his wish. This excessive strain of so many meetings, it told on his health. And 1 month after his 80th birthday, he passed away quietly at his Kolkata home. In fact, you see a picture of all the people accompanying the cortege. In Calcutta, not since the death of Tagore had there been such an outpouring of public grief. So anyway, Bose's body was consigned to the flames, but Bose statistics lives on. Even the photons which are being emitted by those flames, which are being emitted by your screen as you hear me and see me, these all come from, all satisfy the Bose statistics. Now, a little bit before I finish, a couple of minutes, we need to understand Bose properly. See, he was not a modern scientist. He was a complete product of the Bengal Renaissance. He was a mathematician, a physicist, chemist, spectroscopist. He was a great musician. He used to play the esraj. He was a great conversationalist. He did a little bit of his own way of administration after he died at Dhaka University for so many years. He was a man of letters. He wrote very well. He used to love food. He was a family man par excellence. And he was sort of full of the milk of human kindliness. So people would go to Bose and generally get a very good reception. Of course, there have been exceptions. That's true with everyone. We should think of his 1923 work as bridging the gap between the old quantum theory and quantum mechanics. He was still thinking in terms of the old quantum theory, but using the results of quantum mechanics. And in some sense, he could see the results of quantum mechanics. I don't think he saw them clearly, but in the words of Shakespeare, as through a glass darkly, he could sort of guess. He had some intuition to find what the right results were. But he did use them before they were actually well established. But it's clear that when quantum mechanics actually came, he didn't like it. He didn't work on it for many, many years. Still, there was no option except to work in it. And important thing is his great work was not achieved by serendipity or not just by doing some mathematical calculation. It was done by deep reflection and some absolutely amazing physical intuition. So that is where the greatness of Bose lies. In that physical intuition by which he could sort of see the photons and their behavior, which nobody else had been able to see before him. So one of Bose's students in the final years wrote, one should not, Bose of course did many things. One should not expect people like him to be doing routine work in one particular line. That would be insulting him. They, it's people like Bose, are after the final truth, not caring for what can be achieved. He was not interested in small matters, wanted to go to the depths. He was an aristocrat. So it is as an aristocrat of science that we need to remember Bose. So therefore, he was undeniably the founder of quantum statistics and therefore a pioneer of a great deal of modern science. And that is enough. We shouldn't ask what Bose did afterwards. After all, do we ask what did Dalton do after formulating his atomic theory? No, it's Dalton's atomic theory is an all-time great. What did Neil Armstrong do after he set foot on the moon? We don't care. What did Tulsidas write after Ramcharitmanas? We don't care. These are all-time great works, and we remember those great works. And therefore, I will conclude my talk by showing you this is the only color photograph of Professor Bose which exists, together with his famous formula which he derived. And you see him playing the esraj here. And I would like to end this on a note of thanks to Professor Bose for all he gave us, and thanks to all of you, my audience, for having sat through this very long session so patiently. Finally, that's the formula. That's what will remain. When none of us are there, when Bose is completely forgotten, this formula will remain forever. Thank you. Thank you very much.
Thank you, Sreerup. Thank you for this brilliant talk, mesmerizing. So, if there are questions, comments, you can raise your hand, unmute and ask the question.
Yes.
I
All right.
see comment. Is there any question?
Yeah, I'm happy to handle questions. Anybody who wants to ask anything about.
Please unmute and ask the question. I see Punnabrato has raised the hand.
Hi, Sreerup. This is Punnabrato.
Yes.
So I'm just wondering, in his original paper, first paper, which was published by Einstein.
Yes.
So in that paper, that factor of 2 was there, or it was removed, or so? What was the story?
So the factor of 2 was there, and Bose says, see, we don't have the manuscript. Okay, we only have the published paper, because in those days manuscripts were thrown away; they were not returned. Okay, so what Bose said, and he continued to say till the end of his life, that he had written that since these are particles, see, he thought of the photon purely as a particle. So if he thought of the particle as having 2 different states of angular momentum, which can only be clockwise and anti-clockwise rotation.
Right.
Okay. Now, Einstein didn't like that, because Einstein, and it's correct, he thought of the photons as point particles, and how can point particles have 2? It's a quantum mechanical effect, which actually comes from relativity, but that was not understood then.
Okay.
So
okay.
Einstein changed that to polarization. So in the paper it says polarization, and then of course, you know, if you say polarization for a particle, then you are obviously invoking wave-particle duality. Now, one reason which Einstein could do it was that at the same time when Bose sent his paper to him, de Broglie had also sent his paper to Einstein. So it is Einstein's mind which was sort of confused, and he put that in. Now, Bose always said, I didn't write polarization, I wrote angular momentum. But, you know,
no proof as such.
No proof in that sense, because of it is lost.
Okay. Thank you. It was a nice, very nice talk.
Yes.
This is a message from Professor Amitav Raychaudhuri. He said he didn't know many things. So, you know, I think that is true for many of us.
Thank you, Amitav. Thank you so much. So,
it was a great talk, Sreerup. Great talk. Great talk.
Thank you. Thank you.
Yeah, fantastic talk.
Yeah.
Are there any other questions or comments? Anyone from the audience? Anyone from the offline audience? Amitav, maybe you can just.
So I have a very small comment.
Yes.
That he said that the 1924 work of Einstein is the last thing that remains or lasts. I think the gravitational wave paper is later.
Okay. Yeah, that could be. But you know, gravitational wave paper is only a small development of the GR work. Yeah. So after that, from 1925 onwards, Einstein was mostly working on his unified field theory.
Yes, absolutely.
And as you know, that was a sort of dead end unified. Well, actually, the EPR paper came after that. I'm not being completely fair. The EPR and all these statistical interpretation papers, those certainly came later.
Yeah, but those are interpretation. The gravitational wave is a physical thing.
Well, EPR is also a physical thing nowadays. In EPR, you know, you have all this quantum entanglement and so on. So it's certainly a real thing. But yes, but these were sort of little things which he did in addition to his earlier work, but not the kind of revolutionary work he had been doing. Of those, this Bose-Einstein statistics is the last of them. So that's essentially what I meant. But yes, you are correct. It's not that he did not publish significant papers after that. Yes.
Any other question or comment? I have a kind of a curiosity. I mean, since you have actually kind of probably you have researched much more than what you have covered in your talk. So as you rightly mentioned, S.N. Bose is probably the only person who was not an institute builder, while
Yes.
all his contemporaries did get into institute building. So why
Yes.
is that? It was his personality, or there were some undercurrent or something?
No, I think he was just a very free-thinking person. To be an institution builder, to be an administrator, to run something, you need to, I don't know, maybe you need to be in some sense disciplined. So he was not a disciplined person. He did what he liked. And in the Dhaka University, he was sort of free to do whatever he liked. He would come in the middle of the night and work with his students. On holidays, he would suddenly disappear. And so all sorts of things. So maybe at the end, I'll tell you one of my favorite stories about S.N. Bose. And it'll sort of give you an impression of the kind of person he was. He was eccentric, no question about that. So there was an occasion when, I think this was 58 elections or something. So in an election day, so people were going out from the university, going to vote and coming back. And you know that when you go to vote, people put this black ink on your nail. Okay. So people discovered that when people were coming back, so Professor Bose, he was coming with a bottle, small bottle from his pocket. He would wear this Punjabi, take a pocket out and a small piece of cotton wool. He put that solution and remove that ink. I said, see, I've removed the ink, you can go and vote again. So he had spent a few days in the chemistry laboratory finding out a reagent which removes that ink. Now, this is childlike, but again, it requires skill and talent to do that. However, I'll tell you the rest of the story. So he then, of course, after some time, this news reached Amherst Street Police Station. So the OC now found national professor is doing this. So you can't send people to arrest a national professor. It would make a scandal. So he came himself. He came to Professor Bose's room. So Bose was sitting and writing something, engrossed in his calculation or something. So, the OC came and stood outside the door with his hands folded like that. So after some time, Bose realizes somebody standing. He looks up and says, what do you want? So he says, I am the OC of Amherst Thana. I came to meet you. Yes, what is it? Say, I hear that you are doing this, you're removing this vote election ink and so on. And Bose says, yes, you want me to do it for you? So he says, no, I think, if you don't mind, can you give me that bottle? So Bose says, you want the bottle? Why? He says, it's actually illegal to do this. So please give me the bottle. Don't do this further. So Bose gave him the bottle. It had not occurred to him that it is illegal to do this. Yeah. So that is the kind of man he was. Okay. So he was not cut out to be an institution builder. Let's say it like that, and he knew it himself.
Thank you. I think that actually really gives a perfect impression of how that man was.
Yes.
Thank you so much, Kim. And it's a brilliant talk, and it's recorded, and it will be in our website. So, whoever wants to listen to it, you are most welcome to share it with your friends and those who.
Sure.
Thank you once again.
Thank you very much. Thank you very much, and thank you everyone for listening.
Thank you. খুব ভালো খুব মন দিয়ে ওর স্লাইড গুলো